In this video, I'm going to introduce you to some basic concepts that can help you understand how to interpret regression in political science. If you're interested in understanding how to read the tables themselves, you should check out the next video on reading regression tables. This video has two purposes. First, to help you understand why we use regression in political science, and second, to help you understand the two important things we use from a regression table: the sign of the results and their statistical significance. Overall, there are two big reasons why I'm having you read statistics and read regressions. The first is that data science is a part of all of our lives now. It's important for everyone to have a basic fluency in reading statistics so that we have a common language we can use to discuss data science. The second reason is that I don't want you to feel like there's any article out there, any research you can't read because you don't know where to start. The purpose of my introduction to regression and regression tables is to help you understand that even if you can't understand all of an academic article or all of research that's out there, you can still get some really important information from it. Regression analysis is one of the most common forms of research in political science. People use it because it allows them to hold variables constant while they compare just two of them to each other. This is powerful because it allows us to eliminate some alternate explanations and get closer to identifying a relationship between cause and effect. If we wanted to better understand the relationship between economic development and democracy, we'd want to make sure that we rule out other explanations. Well, if we think it's the economy, then we have to make sure it's not ethnic diversity or it's not the age of a regime, for example. One way to actually do that would be to compare countries with the exact same level of ethnic diversity and the exact same ages. Then we can look at the levels of economic development in each country, and if the level of democracy is higher in the country with a higher level of economic development, that indicates that there might actually be a relationship there. The problem is that no two countries have the exact same diversity. No two countries have the exact same age. That's why we use math. If we can identify numerical data that represents these concepts, then we can use an equation to artificially hold everything constant, except for one of the variables. To keep going with this example, it might be possible to say that democracy is some combination of economic development, diversity, and age. We could represent this mathematically with an equation. In this equation, democracy is represented by a y as the dependent variable. For some reason in social science, we always put the dependent variable first in the equation. It just is that way. And the independent variable is represented by an x. Just to make things a little confusing, we'll also include any control variables here, those alternate explanations we want to rule out, using the letter x. But they each have a number so that we can tell them apart from each other. To speak more generally again, the effect y is equal to a sum of the cause plus the control variables. The Roman letters represent data that we have. The equation produces two important things for us. First, a number, here represented by beta, of the size or direction of the effect of x on y. So the effect of economic development on democracy is going to be quantified into a number called a coefficient represented by a letter, beta. Control variables get their own betas too, but the other important thing we want to note here is the epsilon at the end, the error. You'll note just FYI, the things the equation produces are all in Greek letters. If we focus on just the relationship between our y, our effect, and one variable, our cause, the beta is simply the slope of a line that best represents the data. The problem here is that we never have an equation with just two variables, just one x. We can't show that to you visually though, because then we're dealing in multiple dimensions. That's why I'm just showing it to you with two variables. When we interpret that coefficient, when we try to understand what that beta actually means, the only thing I want you all to focus on right now is its sign. Is it a positive or negative number? Positive coefficients show positive relationships. For example, as interstate war increases, state development increases. Negative coefficients show negative relationships. This would be a case where as civil war increases, state development decreases. Finally, I wanted to return to that epsilon, to that error term at the end of the equation. First off, I just wanted to remind you that when we're talking about the error in an equation, we're talking about just how much variance there is around that regression line. Some data is all over the map, and while you can draw a line that represents that data, it's not going to be a very accurate representation of what these individual data points might mean and what their relationship is. Other data is really tightly drawn around a line. This would be a case of data with low error or low variance. What we do with that error term is combine it with the overall n. It's the number of pieces of data that were used in the equation, and we calculate a margin of error. Technically, what we do here is called a hypothesis test. Understanding how this works is really important, but you can learn this later on when you take a class on data science or statistics. Here's what I want you to think of. Imagine that what we're working with is a survey of the American public. We want to figure out how many people are going to vote in the next election. And we're going to choose a group of 1,000 people to represent the entire American population. Every time we choose a sample, every time we choose 1,000 people out of this overall population, we're going to end up with different people. And each group is going to give us slightly different answers. If that 1,000 people that we actually chose, if our sample is accurate, it's going to be representative of the overall population. And it's going to give us results that reflect how everyone in the United States would behave. Sometimes, though, just through random chance, we draw a really bad sample. We get a really strange group of people, and they give us really strange answers. The tests that we use in determining whether our results are valid, whether they are what's called statistically significant, tests are designed to give us an estimate that our results are accurate 95% of the time. So 95 times out of 100, when we draw that sample out of the population of the American public, the answers they give us are actually going to reflect what the general American public thinks. That's speaking about surveys specifically. When we speak more generally and when we speak about regression results, the most important thing to know is whether we have any results at all. Essentially, it comes down to, are our results different from zero? If our results are not zero and we can actually tell that within our margin of error, then we're pretty happy. Just wanted to make a side note that 95% sounds like a lot. If we said this a different way, though, it doesn't quite sound so great. 95% confidence also means that there is a 1 in 20 chance, that's a 5% chance, that our research is wrong. So every 1 in 20 times, research might come out wrong for accidental reasons. Maybe the sample was weird, maybe people gave incorrect answers to a survey, or maybe the way a piece of data, like a governance indicator, was put together was just not a great way to think about it. This 95% standard, or 1 in 20 chance of being wrong, is an arbitrary standard, but it's the one we use, so it's the one you'll learn. So there are 3 ways you're going to see researchers refer to error in their research. One is called standard error, sometimes abbreviated as SE. One is called a confidence interval, which we also can call the margin of error. And the last is called the p-value. The confidence interval is the easiest one to interpret and understand. It's the most intuitive. If your confidence interval doesn't include 0, if your margin of error in that graph doesn't cross that line, then it is statistically significant. Unfortunately, this is also the least commonly used way to report error in the research that you're going to read. It's much more common to see people write down standard errors and p-values. The way you interpret standard error is that if the coefficient, if the result itself, is more than 2 times, it's twice the size of the standard error, then it's statistically significant. It's big enough that it outweighs the standard error. The p-value, happily, is the easiest one to interpret. P-values you can think of as the opposite of our confidence range. So a 95% confidence interval is equivalent to a 0.05 p-value. 0.05 just being another way to write 5%. If our p-value is less than 0.05, then our results are statistically significant. So again, these are just 3 different and mathematically equivalent ways to read the same thing. What exactly is the error in our research, and how can I tell if these results are not 0? I'll get more into how to actually read regression tables and repeat how to interpret that statistical significance in the next video on reading regression tables. Before I go though, I just wanted to make 2 quick notes. First, if you are interested in learning more about statistics, I highly recommend the book called Naked Statistics by Charles Whelan. It's extremely readable. It's usually can be found at any bookstore between $10 and $15. And it's also the statistics book that you will read if you take a research methods class in the politics department. The last thing I wanted to say that is if you're confused, it's totally okay. Everyone else is too. Talking to people who do statistics for a living now, most people didn't understand this stuff the first time they learned it. Most people, including myself, didn't understand it the second time they learned it. This is something that makes more sense the more you do it though. So persevere, keep trying, and please come to me for help as well.